In this video, I will talk about the second part of our proof. In the first video, we proved that M has some geometric information by stationary, and in this video, I proved a Poincare type inequality by stability of M. For example, if M is a C2 capitalist surface with a fixed contact angle with omega, then we can prove a Poincare type inequality for such M. And the method is that we use some smooth variation x to test the stability of M, and then we can derive a Poincare type inequality. And now, since we are dealing with a set of finite parameters, which means that M has some singularities. For example, this is M, and the idea is that we still want to test the stability of M by a smooth vector field or a smooth variation. And this variation coincides with the choice we make when we are testing the stability for the smooth capillary surface at the regular part. This vector field coincides with the original vector field we choose for when M is C2. And for those singularities, we will use the fact that the Hausdorff dimension of this singular set is at most n-3 to show that there exist some smooth Cartov functions near the singularities, and by this smooth Cartov functions, we can prove that for any smooth vector field we choose, this vector field has a very small contribution near the singular part of M, so that we can finally derive a Poincare type inequality because this singularity has a very small contribution. And that's what we do in lemma 4.1 in our paper. We use the notations as before and assume that the singular part of M is a closed set with its Hausdorff dimension at most n-3. And we can prove that there exists some small epsilon. We can prove that for any small epsilon, there exists some open sets S prime epsilon and S epsilon in Rn, such that, for example, if this is singular M, if this is M, then the singular part of M can be covered by the small region S prime epsilon, and the bigger region S epsilon is contained in the epsilon neighborhood of the singular part of M. Moreover, we can construct some smooth Cartov function phi epsilon, such that phi epsilon vanishes in a small region and is identically 1 outside the bigger region. And the most important thing is that the L2 norm of the tangential gradient of phi epsilon with respect to M is very small, and it is controlled by epsilon times a constant C2. And if epsilon goes to 0, then this integral will converge it to 0. So it will have a very small contribution to our Poincare type inequality. which converges to 0. And the main tool we will use to construct the smooth Carter function is the monotonicity formula for rectifiable varifold and general varifold with fixed contact angle with the boundary. And precisely, if this is M, and this part means the boundary of M, and this is the interior part of M. Then we can see that these points are the singularity inside omega, and these points are the singularity of M in the boundary of omega. And we will use the monotonicity formula for M as a rectifiable varifold inside omega, and as a general varifold with fixed contact angle with the boundary partial omega for this singularity near the boundary of omega. And let's recall some definitions. First, we recall that the rectifiable varifold. We consider an open set omega in the Euclidean space Rn, and a rectifiable varifold B is defined to be the equivalent class of all pairs, where M is taken to be a unrectifiable set, and theta is the multiplicity function, which is a positive and Hm measurable function. And with this integral finite. And for rectifiable varifold, an important thing is the wet measure mu b. And we say that the rectifiable varifold B has a generalized mean curvature underline H if such formula holds. And from this formula, we see that the rectifiable varifold is an extension of the smooth submanifold M in omega, and where M has no boundary lies in the interior of omega. Because if M is taken to be a C2 smooth submanifold of omega and has a boundary lies inside omega, for example, if this is M, then we can decompose X to be the tangential part and normal part with respect to M, and where the normal part will give us the mean curvature of M. And the tangential part, if we use divergence theorem, we will see that a boundary term here. And since we want this formula holds for any smooth vector field with compact spectrum inside omega, this means that M has no boundary lies inside omega. So this is an extension of the smooth submanifold. And for rectifiable varifold with a generalized mean curvature, which is bounded by some constant lambda, we have the following monotonicity formula, which holds for any bore BR Xi, where Xi is any point inside omega, and BR Xi lies in the interior of omega. And the following formula is the monotonicity formula. And indeed, the right-hand side is always non-negative, which means that this guy is non-decreasing. And now, before we introduce the general variable with a fixed contact angle with the boundary of omega, we will have to first recall some definitions of general variable. Let's consider the most simple case, the n-1 dimensional general variable in Rn. Let U in Rn be an open set, and we set G sub n-1 U to be the product space of U times the Grassmannian. This is the set of all n-1 dimensional affine space in the Euclidean space Rn. And for general variable, it is simply a random measure on this product space. And we let V sub n-1 U to denote the set of all general n-1 variables in U. And for general variable, there are several important things. The first one is the weight measure. We let mu V to denote the weight measure of V. It is a random measure on the downstairs space U, which is in Rn, and it is defined by this formula. Here, phi is taken to be any any continuous function on U with compact support. And if we take phi to be a indicator function of some compact set K in U, then mu V of K is the number which is given by this. It is indeed V of pi inverse K, which is K times the Grassmannian. Here pi denotes the canonical projection of the product space to one of its components. And another important thing is the first variation of the variable. We let delta V to denote the first variation of V, and which is a linear functional of on this function space. And it is given by delta V takes in some C1 function with C1 vector field with compact support in U, and we will have the number given by this formula. And if delta V, we say that V is of locally bounded variation in U if delta V of G is bounded by some constant C times the norm of G, where G has compact support in some compact set W. And such formula holds for any compact set W in U, then we say that V is of locally bounded variation. And if V is of locally bounded variation, we can extend delta V to be a linear functional on the continuous function space with compact support. And then we can use the Reed's representation theorem to see that there exists a random measure delta V on U and a vector valued delta V measurable function nu, whose norm is 1 for delta V almost everywhere, and such that the linear functional delta V of G can be represented by this integral. And here delta V is called the total variation of delta V and is characterized by this formula. And now we can define the general variable with fixed contact angle, with constant contact angle. We take V to be a n-1 general variable with a finite wet measure, mu V of omega. When we fix a given Hn measurable set B plus in the boundary of omega. For example, if this is B plus, we fix, and we fixed a contact angle theta, then V is said to have a fixed contact angle theta with the boundary of omega of B plus if the following two conditions holds. And for such two conditions, they reveal the geometric information of such variables, and we can and we have some kind of formula in our first part, and so we can see that such definition of general variable is an extension of C2 capillary surface with a fixed contact angle. And for such variable, we have the monotonicity formula. If the generalized mean curvature is in LP near the tubular neighborhood of omega, then such monotonicity formula holds. And here, B tilde R means the nonlinear reflection of BRX with respect to the boundary of omega. Precisely, if this is omega, and we have a bore BRX here, just outside of omega, then we can reflect it with respect to omega and have a BR tilde X. This is a nonlinear reflection. And now we can start our proof. First, since the singular part of M is closed and is apparently bounded, so it is compact, then by the fact that the singular set of M is Hausdorff dimension at most n-3, we can use the definition of Hausdorff dimension and notice that the singular part of M is compact, and we can cover it by finitely many bores, which is collected by G. And here the bores have the center Zi, which lies in the closure of omega, and the radii of these bores satisfies this formula by the Hausdorff dimension. And we define a subset n epsilon in the Euclidean space by the S neighborhood of partial omega. And now we divide this covering bores by the interior bores, which has a strict distance to the boundary, and the boundary bores by the collection of these bores minus the interior bores. And now for the interior bores, for the interior covering bores, we view M as a rectifiable varifold. And we can see that by part 1, M has a generalized mean curvature because this formula holds in part 1. And here, H is a constant, so it is apparently bounded, and we can use the monotonicity formula to find that for any interior covering bores, this formula holds. The Hausdorff measure Hn-1 of this guy is bounded by C3 times the radius to the n-1. And for the boundary bores, first we notice that for Hn-1 measurable countably n-1 rectifiable set M, we can define a nature n-1 general variable with respect to this rectifiable set M, and it is defined by this formula. Here phi is taken to be any continuous function with compact support on the product space. This is U times the Grassmannian. And here, tangent Mx is the approximate tangent space of the rectifiable set. So it exists for Hn-1 everywhere on M. And in this case, we can check that the wet measure of such general variable is simply the Hausdorff measure restricted to M. And also, we can check that the first variation of such general variable is takes in some smooth vector field with compact support G is given by this formula. And now we view M as we relate M to a general n-1 variable near the boundary. And we can prove that M is a general variable with a fixed contact angle by part 1. Since in part 1 we prove these two formula holds. And that we can check the definitions of the general variable with fixed contact angle. And moreover, we know that the generalized mean curvature edge of such variables is bounded, is a constant, so it is apparently LP near the epsilon, near the tubular neighborhood of omega. So we can use the monotonicity formula and to see that for every boundary bore, this formula holds. In conclusion, for any covering bores, either near the boundary or inside, we have this formula holds for any covering bores. So by this, we can construct the smooth Carter functions. First, we construct smooth Carter functions near every covering bore by defining phi I to be vanishes inside BRIZI and identically 1 outside twice the radius of the concentric bore. And where the gradient of such smooth Carter functions is bounded by 2 over Ri. And now we want to have smooth Carter functions by gathering these smooth Carter functions together. First, we define phi tilde epsilon by taking the minimum of each smooth Carter functions at x. So phi tilde epsilon is piecewise smooth, and which vanishes at here and is identically 1 outside the union of twice of the radius of the concentric bores. And now we can check the L2 norm of the tangential gradient of phi tilde epsilon. It is bounded by the gradient, and we can and by the covering property, it is bounded by this summary. And since gradient phi I is identically 0 in BRI, so we can have this inequality. And finally, since gradient phi I is bounded by 2 over Ri, and the Hausdorff measure of this set has an upper bound, so finally we can have that the L2 norm of the tangential gradient of phi tilde epsilon is bounded by some constant times epsilon. Since phi tilde epsilon is only piecewise smooth, we have to finally modify it to obtain a smooth Carnot function phi epsilon. And and after modifying, we can have the desired smooth Carnot function, which completes the proof of this step.